Good afternoon and welcome to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Malihe Yousofzadeh from the University of Isfahan in Iran, who will talk about finite weight modules over affine superalgebras. Please.
Thank you very much for the introduction. I would like to thank the organizers of this series of seminar to give me such an opportunity to deliver a talk. As it was mentioned, today I want to talk about finite weight modules over affine superalgebras. As I didn't know the background of my audiences, I will start with some elementary definitions, and then step by step, I go through the main body of the talk. Throughout my talk, all vector spaces are considered over the field of complex numbers. I will frequently use the concept superspace. By a superspace, I mean a vector space which is decomposed into two subspaces, V0 and V1. And the zero part is called even part, and the one part is called the odd part. An element of, when we have an element of V0, we say that X is even and has degree 0. And we denote it with this notation. And if X is an element of V1, we say that it is odd, it has degree 1, and denote it with this notation. I also would like to make a convention that if I will talk about the degree of an element, I assume that X is either an element of V0 or an element of V1. Suppose that L is a superspace with 0 part L0 and 1 part L1. And suppose that S star is a bilinear map from L times L to L. We refer to this star as a product. We call L a superalgebra if this star is compatible with the grading. It means that Li star Lj is a subset of Li plus j. Here, I plus j is just the summation in the group Z2. Okay. The superalgebra L is called supercommutative if A star B equals B star A with this coefficient, -1 power degree A degree B. And you can see that if A and B are of degree 0, this coefficient disappears, and we just get commutativity. The superalgebra L is called anti-supercommutative if A star B equals -1 power degree A degree B B star A. The difference between supercommutativity and anti-supercommutativity is the existence of this minus here. Finally, an anti-supercommutative superalgebra L is called a Lie superalgebra if this identity is satisfied. The identity says that X star Y, then star Z equals X star Y star Z minus -1 degree X degree Y, Y star X star Z. If you look at the order of X, Y, Z, on the left-hand side and on the right-hand side, you see that on the left we have X, Y, Z, and in the right, we have two terms. One of them is XY, and the other one is YX. The order of XY is changed, and this coefficient appears. It is usual that instead of a star in a Lie superalgebra, we use brackets. So when we are using a bracket, it means that we are working with a Lie superalgebra. Subalgebras, ideals, and quotient superalgebras are defined in the usual sense. I mean, everything must be in the supersetting. We also note that if L1 is 0, we have here L equals L0 direct sum L1. And if L1 is 0, we just get L equals L0. In this case, we just get a Lie algebra. As a simple example, if a vector space V is considered with a 0 Lie bracket, I mean the bracket of each two elements is 0, then we get a Lie algebra that we call it an abelian Lie algebra. Let's look at another example. Suppose that m and n are two positive integers, and we take G to be the set of all block matrices like A, B, C, D, in which A is an m times n matrix and D is an n times n matrix. We can consider G as a super space if we define G0 to be the set of all block diagonal matrices and G1 to be the set of all block off diagonal matrices. This G is a super space, and we can define a Lie bracket on this superspace. Just maps the pair XY to the product, usual product XY minus -1 degree X degree Y, usual product YX. By usual product, I mean that we have some matrices and we can make the product of two matrices. So XY and YX appearing here are just the usual matrix product. This G, together with this Lie bracket, is a Lie superalgebra that we denoted with GLMN. Sometimes we can have another examples. For example, suppose that we have a Lie superalgebra, and using this Lie superalgebra, we can form another one. Just make the tensor product of G and Laurent polynomials. This new G hat has a Lie bracket defined as follows. Just define the product of X tensor Tn and Y tensor Tm to be the Lie bracket of XY tensor Tn plus M. The Lie bracket here is just the Lie bracket on the old Lie superalgebra. It is easy to see that G hat together with this Lie bracket is also a Lie superalgebra. When we are working with algebraic structure, we can talk about morphisms. Suppose that we have two Lie superalgebra L and G. A linear map from L to G is called a homomorphism if phi preserves the degree. It means that phi of L0 is a subset of G0, and phi of L1 is a subset of G1. And the second condition is that phi preserves the bracket. It means that phi of bracket XY is the bracket of phi X, phi Y. And as in the left-hand side bracket is the bracket on L, and the right-hand side one is the Lie bracket on G. The main topic of my talk is the module theory of Lie superalgebra. So let's see what is the definition of a module for a Lie superalgebra. Suppose that L is a Lie superalgebra. A superspace V together with a bilinear map dot from L times V to V is called an L module if there is a compatibility with this dot and the grading. It means that LJVI is a subset of VI plus J, and again, by plus I plus J is just the plus in the group Z2. And we should have the action of bracket of XY on V equals the action of x on the action of y on v minus -1 degree x degree y, the action of y on the action of x on v. Again, here we have xy, and here we have yx. We change the order of xy in these two terms, and this guy appears. Okay, now I wanna also define a module for an associative superalgebra. An associative superalgebra is just a superalgebra whose product is associative in the usual sense. A superspace V together with a bilinear map from an associative superalgebra times V to V is called an L module if, again, there is a compatibility with this action dot and the grading, and also we have this. The action of xy, by xy we mean the product of two elements of L. The action of xy on V equals the action of x on the action of y on V. And as you can see, it seems that working with modules over associative superalgebras are easier than working with modules over Lie superalgebras. Submodules, simple modules, and quotient modules are defined in the usual sense. Again, everything must be considered in the supersetting. There is a very important and vital point regarding modules over Lie superalgebras. Corresponding to each Lie superalgebra L, there exists a specific associative superalgebra called the universal enveloping algebra of L. We denote this specific associative superalgebra by UL. The important point is that there is a one-to-one correspondence between L modules and UL modules in a prescribed way. If you have an L module, you get a UL module, and conversely, if you have a UL module, you have an L module. And this correspondence, as I mentioned, is in a prescribed way. Okay, let's look at an example of a module for a Lie superalgebra. Suppose that L is a Lie superalgebra and G is a subalgebra of L. We can consider L as a G module via this action, mapping Hx to the Lie bracket of H and X. In this case, we say L is a G module via the adjoint representation. So whenever we have a Lie superalgebra, we can consider that Lie superalgebra as a module over each subalgebra of that Lie superalgebra. Now, suppose that L is a Lie superalgebra and G is a subalgebra of L. Assume we have an L module via the action dot from L times V to V. For each X belong to G, we can define pi of X to be a map from V to V, which maps V to X dot V. This pi X is a linear transformation. Now, if we consider all such linear transformation together and assume that these linear transformations are simultaneously diagonalizable, we say V has a weight space decomposition with respect to G. When we say that these linear transformations are simultaneously diagonalizable, we can talk about common eigenspaces. In this case, each common eigenspace is called a weight space. And we can decompose V to the common eigenspaces. Here, V equals direct sum V lambda, where lambda is an element of the dual space of G. And each V lambda is a common eigenspaces provided that this is non-zero. So each V lambda here is just a common eigenspace of these linear transformations. If all weighted spaces, we refer to each of these common eigenspaces a weighted space. If all weighted spaces are finite dimensional, we say V is a finite weight module, of course, with respect to G. And if V lambda is 0, we say lambda is a weight of V. So let's return to our example as a module via the adjoint representation. Suppose that L is a Lie superalgebra and G is a subalgebra of L. We can consider L as a G module via this action, which is the adjoint representation. If in this case, L has a weighted space decomposition with respect to G, the set R of weights of L is called the root system of L. And instead of saying L has a weighted space decomposition, we say L has a root space decomposition. So what we have L, a Lie superalgebra, we have G, a subalgebra of L, and we assume that L has a root space decomposition or weighted space decomposition with respect to this G. So we can decompose L into common eigenspaces. These common eigenspaces are labeled with a subset that we refer to as the root system, and this subset is a subset of the dual space of G. This R is very important for the study of module theory of Lie superalgebras. Let's look at another example. Suppose that L is a positive integer greater than 1, and G is the set of all block matrices like X, A, B, C, D, in which A, B, C, and D are L times L matrices. We assume S is the set of all elements of G with supertrace 0. For a matrix X, block matrix X, supertrace of X is defined to be trace of A minus trace of D. And Rs is the set of all such matrices with supertrace 0. This S is a subalgebra of GL-LL. And if we look at Ci, I here is the identity matrix, and Ci is the set of all coefficients of I. This Ci is an ideal of S. So S is not simple, but if we make the quotient of S over Ci, we get a simple Lie superalgebra. This simple Lie superalgebra is denoted with PSL-LL. We refer to this simple Lie superalgebra as a basic classical simple Lie superalgebra of type A, L-1, L-1. P is a Lie superalgebra, so we have a 0 part, we have the odd part, and inside the 0 part, we can look at the set of diagonal matrices. Our Lie superalgebra P has a root space decomposition with respect to this H. I talked about basic classical simple Lie superalgebra, and I introduced type AL-1, L-1. But in general, there is a definition for basic classical simple Lie superalgebra. In fact, if we have a finite dimensional simple Lie superalgebra, we say this simple Lie superalgebra is a basic classical simple Lie superalgebra if the 0 part is a summation of an abelian Lie algebra and finitely many simple Lie algebras. In other words, G0 is a reductive Lie algebra. And also G is equipped with a non-degenerate bilinear form satisfying some condition. The first condition is that the form of xy equals -1 degree x degree y, yx. In this case, we say that the form is supersymmetric. The second condition is that the bracket can move through the form we say that the form is invariant. And the last one is that the zero part and the odd part are orthogonal with respect to the form. We say the form is even. Basic classical simply superalgebras are classified. There are known as types A, B, C, D, E6, 7, 8, G2, F4, and other types ALL, ALK, BKL, and so on. These ones, A, B, C, D, and so on, are some basic classical simply superalgebras for which the odd part is 0. And the second line contains the ones for which the odd part is non-zero. Again, here we have a Lie superalgebra, we have the zero part, we have the odd part, and inside the zero part, we have a subalgebra with respect to which G has a root space decomposition. Now suppose P is the basic classical simply superalgebra and form P hat, which is the tensor product of P and Dolan polynomials. Then we make the direct sum of P hat with a 4-dimensional vector space spanned by C1, C2, D1, D2. There is a prescribed Lie bracket on this L in which C1 and C2 are central and D1 and D2 acts as derivation. This Lie superalgebra, together with the mentioned prescribed Lie bracket, is a Lie superalgebra called non-twisted affine Lie superalgebra of type ALL1. Again, here we have a Lie superalgebra. So we have the zero part, we have the odd part, and again, inside the zero part, there is a subalgebra we refer to as the standard Cartan subalgebra, with respect to which L has a root space decomposition. Sorry, my laptop is out of the charge. Okay. In this slide, I introduce non-twisted affine Lie superalgebras of type ALL1. We have other kind of affine Lie superalgebra that I will introduce in my next slide. In fact, suppose that G is a finite dimensional basic classical simple Lie superalgebra of type X, which is not ALL. In my previous slide, I was talking about type ALL, and in this slide, I suppose that X is not of type ALL. Suppose that H is a subset of G0, and it is the standard Cartan subalgebra of G. My G is a basic classical simple Lie superalgebra, so it is a non-degenerate, it has a non-degenerate supersymmetric invariant even bilinear form. I call it kappa. I also assume that sigma is an automorphism of order n such that it preserves H and it is preserved by the kappa. It means that kappa sigma x sigma y equals kappa xy. The automorphism sigma induces an automorphism on G hat. G hat is the tensor product of G and Laurent polynomials. This sigma hat, which is the extension of sigma, is defined in this way. Sigma hat x tensor Tm equals zeta minus n sigma x tensor Tm. Zeta is the primitive root of unity. Now assume L is the fixed point subalgebra of G hat under sigma hat, and consider a 2-dimensional vector space CC direct sum CD. Then we can form the direct sum of L this L, and this two-dimensional vector space. This G has a specific Lie bracket for which D acts as derivation and C is a central element. We refer to this C canonical central element of G. If sigma is the identity map, G is called a non-twisted affine Lie superalgebra of type X1. And if G is of type AL, DL, E6, AKL, DKL, there is a certain automorphism sigma such that sigma is of order 4, 3, or 2, depending on the types appearing here. Now, if we consider the corresponding G for this sigma and these types, we get a Lie superalgebra that is referred to as twisted affine Lie superalgebra of type Xn. I introduced affine Lie superalgebra. Some of them are non-twisted and some of them are twisted. But in general, affine is something that I told you, it's according to the classification. In fact, affine Lie superalgebras are defined by generators and relation, and they are classified. And something that I told you, it is the result according to the classification. But in spite of, and apart from what is the definition and what is the classification, all affine Lie superalgebras have some common properties. And these common properties are important for my talk. So I suppose that G is an affine Lie superalgebra of type Xn. The first property is that G is a Lie superalgebra. So we have the 0 part, we have the R part, 1 part, and again inside the 0 part, we have a subalgebra, which we refer to as the standard Cartan subalgebra, and with respect to which G has a decomposition into common eigenspaces as before. And these eigenspaces are labeled with R. This R is a subset of H star, and it's called, as I said before, the root system. So we have this decomposition. This R is very important. This R is very important in module theory. I will talk about it later on. There is a symmetric, the first property, I said that there is a subalgebra inside the 0 part, and G has a root space decomposition with respect to H. The second property is that there is a symmetric bilinear form on H star. And the next one is that R has a decomposition like this. We have two kinds of decomposition for R, this one and this one. These two decompositions are very important. In the first decomposition, we have R equals Z delta. Here, delta is an element which is orthogonal to entire root system with respect to this form. And the second part is this. We have union of some subspaces. These subspaces are labeled with the elements of a finite set of H star. And we can see some K alpha dot and R alpha dot. These two elements are two non-negative integers. At present, these two integers are not important, but they appear in these subsets. And also, we have decomposition for R as the union of three subspaces, R imaginary, R real, and R NS. R imaginary is just Z delta. It is the set of all elements which are orthogonal to the entire root system R. R real is the set of all elements which are not self-orthogonal. We refer to these elements real roots. And the last one is the remainder part. In fact, R and S is the set of all elements of R which are self-orthogonal but are not an element of R imaginary. The first difference between superlevel and non-superlevel is the existence of this part. When we are working with non-super affine Lie superalgebra, I mean that the even part is 0, this part R and S will vanish. And we just have R equals R imaginary union R real. The next property is that the 0 part of our affine Lie superalgebra has a decomposition into two subspaces, G and T. At present, T is not important for my talk, but G is a summation of 1, 2, or 3 affine Lie algebra. It says that inside the 0 part of an affine Lie superalgebra, there are some affine Lie algebras. So in the 0 part, we have some affine Lie algebras, 1, 2, or 3 affine Lie algebra. I should mention that the case R equals 3 happen just for some non-twisted cases. So if we are working with a twisted affine Lie superalgebra, inside the 0 part, we have either 1 affine Lie algebra or 2 affine Lie algebra. Okay, as I told you, this R is very important for the module theory. In this union, we have some R dots, and for this R dot, I also want to define R dot real. R dot real is the set of all elements of R dot which are not self-orthogonal. Now look at this part. Corresponding to each alpha dot, we have this part. And if we let the coefficient of k alpha dots runs over Z, we get a chain. So corresponding to each alpha dot, we have a chain. Alpha dot plus R alpha dot delta. On the right-hand side, we have K alpha dot delta, 2K alpha dot delta, and so on. And on the left-hand side, we have minus K alpha dot delta, minus 2K alpha dot delta, and so on. This chain is very important. In fact, it has a crucial role in the module theory of affine Lie superalgebras. In my talk, I want to focus on finite weight modules over affine Lie superalgebra. I assume G is an affine Lie superalgebra with a standard Cartan subalgebra H and root system R. And I suppose V is a simple G module having beta space decomposition with respect to H. And I suppose that all subspaces, all beta spaces are finite dimensional. There is a very easy lemma says that if alpha is an element of R real, I mean that alpha is not 0, alpha is not orthogonal to itself, and X is an element of G alpha, X acts on V either locally nilpotently or injectively. If X acts locally nilpotently, we refer to alpha as locally nilpotent, and if this X, which is an element of G alpha, acts injectively on V, we say alpha is injective. So if we return to this chain, the elements of this chain are real. So according to this theorem, the elements of this chain is either injective or locally nilpotent. But we can prove a theorem. We show that 3 cases can happen for this chain. The first case is that all the elements of this chain are injective. The second case is that all the elements of this chain are locally nilpotent. And the third case is that there is a point in this chain such that on the right-hand side, all the elements are injective, and on the left-hand side, all the elements are locally nilpotent. And the last one is that there is a point in the chain on the right-hand side, all the elements are locally nilpotent, and on the left-hand side, all the elements are injective. If the first two cases happen, if all the elements of the chain are injective or all of them are locally nilpotent, we refer to the elements of the chain as tight. And if the third and the fourth cases happen, we refer to the elements of the chain hybrid. So for all elements, either they are tight or hybrid. I remind you that I am working with a twisted affine Lie superalgebra, and the zero part was a decomposition as G direct sum T. G is a summation of one or two affine Lie algebras. We refer to this G1 and G2 as affine components of G0, and we denote the root system by R1 and R2. Now suppose V is a simple finite weight G module. We note that the canonical central element of G acts on V as a scalar. This scalar is called the level of V. To study simple finite weight G modules, the following are important. If the level is 0 or not, if this R is 1 or it is 2, if all real roots are hybrid or there exists some tight roots, if R is not 1 and there are some tight real roots, if these tight roots appear in both R1 and R2 or not. The classification of modules over affine Lie superalgebra strongly depends on the answering these questions. Okay, suppose that, I just recalled that the root system of the affine components is denoted by R1 and R2. And as I mentioned, the set of R real is the union of the elements which are injective and the elements which are locally nilpotent. And of course, we can make the intersection of this equality with R1 and R2. A simple finite weight G module is called hybrid if all real roots are hybrid. I remind you that real roots are either hybrid or tight. If all real roots are hybrid, we refer to V as hybrid, and we refer to it as tight if all real roots are not hybrid. I mean, some of the roots are tight. And we call it integrable if R real equals R, L, and V. It means that this part vanishes and we just have R real equals R, L, and V. And we call it quasi-integrable if for a choice of ij as 1 and 2, all real roots of Ri are hybrid, while all real roots of Rj are locally nilpotent. It is proved that if R equals 2, there is no integrable, simple finite weight module of non-zero level. So to study this part, if non-zero level, if we have non-zero level, the level of the module V is non-zero, there is no integrable simple finite weight module provided R equals 2. This has been proved by Rao in 2003 for non-twisted cases, and there is a preprint for twisted cases. This theorem, in fact, motivates us to define these quasi-integrables. Okay. To study and classify finite weight module over affine Lie superalgebra, I need a definition. Suppose that P is a subset of R. We refer to it as a parabolic subset if R is the union of P and minus P, and the intersection of R and P plus P is a subset of P. Now, suppose that P is a parabolic subset of R, and suppose omega is a simple finite weight module over G null. By G null, we mean direct sum of G alpha when alpha runs over P intersection minus P. Omega is a simple module over this G null. Now, we consider B. B is direct sum of G alpha when alpha is an element of P. I can decompose this B into two parts. The first part is G alpha, direct sum of G alpha when alpha is an element of P intersection minus P. And the second part is direct sum of G alpha when alpha is an element of P but not minus P. I have a module omega is a module on this part. I can extend the module action on B just by defining the module action for this part to be 0. Now I have a module over B. As you remember, at the beginning of my talk, I told that when we have a module for a Lie superalgebra, we have a module for the universal enveloping algebra. So omega is a B module, so it is a UB module. And I can make this tensor product of UG over UB of omega. Omega is a module over UB, and this M is a module over UG. And again, as we have a UG module, we have a G module. We start with a simple finite weight module over G null, and we get a module over G. This M has a unique maximal submodule N intersecting omega trivially. So we can make the quotient M over N, and as this N is maximal, this new module is simple. We start with a simple finite weight module over G null, and we get a simple module over G. We say a simple module is parabolically induced if it is isomorphic to such a quotient. Parabolically induced modules are very important in module theory. In fact, it is very important to know if a simple module is parabolically induced or not. Because if you can show that it is parabolically induced, then you can reduce the classification to the classification of some other modules, which are sometimes easier, or you can reduce them to some known results. We show that if we are working with a simple finite weight module over an affine Lie superalgebra G, If V is hybrid, V is parabolically induced from a simple finite weight module over a finite dimensional basic classical simple Lie superalgebra and an abelian Lie algebra. We also proved that if V is quasi-integrable, again, V is parabolically induced from a simple finite weight module over a finite summation of basic classical simple Lie superalgebra and an abelian Lie algebra. And also, we showed that if V is tight under some mild condition, again, V is parabolically induced from some other modules, which and we can, in fact, we can reduce the classification to the modules over another class. And also, we give a recognition theorem for quasi-integrable modules over twisted affine Lie superalgebras. To do so, the concept of a base is very important. A linearly independent subset pi is called a base if pi is a subset of R, and each element of R can be written as a linear combination of the elements of pi whose coefficients are all non-positive or all non-negative. In non-super case, up to plus minus, all bases are conjugate under the while group action, but it's not the case in the super level. So if you want to study and determine bases, we first define a group called quasi-while group, and then classify bases up to the action of quasi-while groups. In this table, I listed the root system of affine Lie superalgebra. You can see Z delta here. Delta is orthogonal to the entire root system. You can see epsilon I and delta P. The form of epsilon I, epsilon J is delta Kronecker of I and J. And the form of delta P, delta Q is minus delta PQ. And we can determine exactly the basis for affine Lie superalgebra. As you can see, against the case in non-super level, we have different bases here up to conjugacy. And using this classification of bases, we can give a recognition theorem for quasi-integrable modules over twisted affine Lie superalgebra. Thank you very much. I want to stop here. Thank you.
Thanks, Malihe, for your interesting talk. Are there any questions, comments, or remarks? Okay, if not, let's thank the speaker again.
Okay, thank you very much.
Thank you. And we will resume on next Monday at the usual time.
Okay.
Bye-bye.
Thank you.
Thank you.
Bye-bye.
Bye-bye. Bye-bye.
Bye, everybody.